We can use technology on this problem. So we need the area of the inside of one loop. So that's going to be as r goes from 0 to 0, by which I mean at some point r will be 0, and then theta will increase, and eventually r will become 0 again. So let's go ahead and find when r is equal to 0 here. We have that. So we're looking for theta when the cosine of this entire angle is 0. The cosine ratio is 0 at these benchmark angles, pi over 2 and 3 pi over 2. And of course, every pi after that in either direction from those points. But we'll just keep repeating each loop. So let's start at pi over 2 and go to 3 pi over 2. So we'll consider the graph of r as the angle goes from pi over 2 to 3 pi over 2. But the angle that we're taking the cosine ratio of is 2 theta. So these angles will be equal to 2 theta, so that theta will be pi over 4 and 3 pi over 4. Remember, we can use technology, so we can look at that graph just on that domain, and we'll see that it's the bottom petal of this flower. So now we can find the area easily using the good old formula for polar areas, which comes from the sector formula of circles, which is 1/2 radius squared times the angle of rotation. So here we go in polars. The definite integral from pi over 4 to 3 pi over 4 of 1/2 r squared, and r squared was defined exactly as 4 cosine of 2 theta, and then d theta. And that's how we do number 47 in section 11.3.